Right, so right now we're going to be doing a little lesson on gases and gas laws and all that fun stuff. Now, earlier in I think the very first video actually, I will have talked about the uh, the kinetic theory of gases, and basically there's 5 points to it. It assumes that all gases occupy negligible volume, they have no attraction for each other, and a gas will fill to expand its container, um, because all no wait let me try that again. Um, it's firstly assumed that the gas has no attraction for each other, so there's no intermolecular forces that's causing any forces of attraction between the particles, and it's assumed that they have negligible volume. Um, it assumes that they're randomly moving around, and as a result of randomly moving around, they fill to occupy a space, and as a result of the previous two, a gas will exert a force on the containers of the walls. They will have inelastic collisions with the walls, and therefore pressure will be exerted on the walls of the container. So it'll exert a force on the outside of the container, pushing outward the molecules of the gas. I mean, so here are the variables that you'll use for. So the symbol of the variable is V. For temperature, it's T. For pressure, it's P. For moles, it's N. And then common units are cubic decimeters, liters, and temperature Kelvin or degrees Celsius, and pressure you get kilopascal or atmosphere, and so on. Pressure equals force per unit area, and so some factors that might affect the pressure of the gas are the number of particles. So if you have more particles, they will exert more net force, because although each particle is exerting the same force, since you have more of them, there's more net force overall. And then lastly, the temperature of any particle. So as we discussed earlier, temperature is the average kinetic energy. So if you give it more kinetic energy, they'll move faster, and therefore they'll collide with the walls with more force. So each particle exerts more force individually, despite being the same. And then we come across the Avogadro's hypothesis, which basically states that equal volumes of an ideal gas at the same temperature and pressure contain the same number of particles, and this is sort of where he built the concept of the mole up. Molar volume at standard, and oftentimes, because gases can change volume and so on, given the temperature and pressure, as we'll go on to discuss later, we use standard conditions known as standard temperature pressure, which is standard temperature is 0 Kelvin, standard pressure is 100 kPa. You can also use standard air temperature pressure, or STAP. The only difference there is that the temperature is measured relative to room temperature, which is 25 degrees centigrade, or 298 Kelvin. The molar volume of an ideal gas at STP is 22.7 liters. Molar volume is just the mole of 1 mole of gas. Now we're going to talk about gas laws. Just checking a Discord message, sorry about that. We're going to be talking about gas laws. There are several that you should know about. You don't need to know the names, but you're expected to know the concepts behind them. So volume and temperature are proportional to each other. That's the first one you're expected to know, that volume and temperature are proportional to each other. What do I mean by proportional? I.e., if you double one, you double the other. The reason this is physically is that as you increase the temperature, right, the molecules move faster, so therefore they will move farther in a given time, and as a result of traveling further, they'll occupy more space. What's important to note here is that they will also exert more pressure on the wall since they have more energy. So this relationship only holds true if the pressure is held constant. So if there's a constant force per unit, if there's a constant force being exerted on the walls, if you keep it the same, then increasing the temperature means that you have to increase the space that you give the particles to move around. So that's sort of what we quote here. The third gas law, I know, great with names, basically states that pressure and temperature are proportional, provided the volume is held constant. The reason for this, again, is fairly simple. When you increase the temperature, you increase the kinetic energy of the particles, they move around faster, and since they can't expand to fill more space. Say you have a rigid container. Since they can't expand to fill more space, what they do is they just push and push, and they try and get that extra space that they want. But obviously, as a result of pushing harder and harder, you create a larger and larger force. And since we define pressure as force per unit area, and since the area, like the surface area of the container, is constant, there's going to be more force, and there's more force exerted on the walls, the pressure is going to be higher, sort of as a result of that. So there's that. Proportional just means linear relationship, where A is a constant. The last one you're expected to know is really the last one that's really worth caring about is Boyle's law, which basically states that pressure and volume are inversely proportional to one another. So by inversely proportional, I mean if you double the pressure, you have the volume, so on and so forth. So 1 over whatever. So P times V is A, that's what I mean here. And the reason for this physically is quite simple. If you have, assume at the same temperature and the same number of particles there, on the assumptions that that's met, if you give them more space to move around, they'll have more space to move around, and they'll hit the walls with less kinetic energy since they used it to do useful work to, i.e. move. And then similarly, if you compress it, if you lower the volume around, there's less space for the particles to exist, and therefore they collide with the walls more often. And then the inverse is true, that if you give them more space, the particles will collide with the walls less often, resulting in less net pressure, because there's less force being exerted on it per unit time. There's less force being exerted on it since there's just less numbers of particles bouncing on the walls. And the inverse is true. If you close the container up, they will hit the walls more often, and therefore there's more force per unit time. There's more force being exerted because more particles are hitting the wall. We can combine these relationships to get the combined gas law, which is this, and it's more or less just combining some of those ideas around. And then lastly, we need to know about Dalton law of partial pressures, which basically says that the pressure of each individual gas, the sum of the pressures of each individual gas is the total pressure in the container. So pressure total is the pressure of gas A plus the pressure of gas B plus the pressure of gas C, and so on and so forth. Alternatively, if you know the total pressure, and you know the ratio of each, what ratio they're combined in each gas is, you can get the pressure of each individual gas. But what we now come to is the ideal gas law. So we talked about volume being proportional to temperature, inverse to pressure, and lastly, we need to know here that volume is proportional to moles. I think that's straightforward. If you have more particles, they need more space, and they occupy more space, and therefore the volume goes up. I think that one's pretty obvious, but intuitively. So since we know that, and we know that P times V is a constant, since we know these three, then we know that volume is proportional to this product here, and then converse is true. PV is proportional to NT, and then we have the ideal gas law, which is PV equals nRT, where R is known as the universal gas constant, which is given in the data booklet. Stoichiometry with gases. At constant temperature and pressure, volume is proportional to moles, so you can essentially do the mole ratios with the pressures, and then you can essentially do, if you're given volumes, provided the temperature and pressure are constant, since these are proportional to each other, you can do the mole ratios with volumes, and you can also do the mole ratios with pressures, provided these things hold true. So for example here, what I mean by that, so consider this reaction here. What's the pressure of oxygen? What's the pressure of water after the reaction is completed? So we know that pressure is proportional to moles, and since we're told here that assumed that the temperature remained constant and was high enough, blah blah blah. We are told that those things are held constant. So initially, the change. So since there's a limiting reagent, this is all used up. 1 times 2 is 2.3, and we have 2.42 initially, and we have 0.12 left. So, and that's the total pressure of the container. Lastly, we need to talk about deviations from ideality. The ideal gas law is based on the kinetic theory of gases, which states, among other things, that gases have no volume and gases exert no forces on one another that are attractive. So, rearranging this, we should get PV over nRT is 1, and this is what we sort of get. This is what we get in the real world. We note here that the pressure is actually less here because actual gases will exert intermolecular forces on each other and try and pack and lower the pressure. And then similarly here, at this point now, the volume of the gases need to be considered. So greater than 1, less than 1. So less than 1 here, that's due to intermolecular forces. And this is due to the fact that gases occupy volume in the real world. Sample questions are pretty straightforward. I might just do a worksheet video sort of outlining some calculations, but they're all pretty much plug and chug with the formulas. You can probably derive most of the formulas provided you know the theory behind it, which I hope I've been able to explain well enough in this video. So yeah, with that in mind, thank you for watching, and yeah.